Hello everyone, welcome to linear modeling part of this entire module. So till now you all must have had some idea about data science, how to load in your data, how to clean your data, and then how to extract various plots and visualize your data and to get more intuition in general about your data. So in this module, we'll go ahead and build on that concept and we'll try and model things. We'll try to learn. We'll try to predict from our data. So what is predictive modeling? So in a data science pipeline, when you have all the data, you have collected it, you have explored everything, you have cleaned it. So then after that comes modeling, and it is a process in which you use statistical or machine learning tools to either understand something or identify some pattern in something, or you to even make prediction on the future. So those are the things that you can do with predictive modeling. And then one of the most important things for any kind of modeling is that the data that is related to your project is actually available. And the learning process will only take place once the model learns from the data. So data plays a very big part in the results that you obtain. So that's why cleaning your data and exploring the features and what is important to you is very essential to building a very good model. Now, there are three types of main learnings. So statistical learning, machine learning, and deep learning. So statistical learning, all these three are different to each other based on a few things. So how much data do you have? So if you have very small amount of data, you probably won't be able to do any machine or deep learning. And if you want your model to be very interpretable, if you want to know, okay, this is the relation of this response to this predictor, or this is how these things are related, then your best bet is statistical learning, because much as you go into machine and deep learning, the interpretability of your model goes very low. And also the extent of manual effort you want to put in to select the features, because in statistical modeling you have to perform EDA, you have to perform correlation analysis and stuff like that to get a sense of what features are important to your actual prediction. So if you want to predict something, you have to know from your data which of these things influence my result. Whereas in machine learning, you don't have to, in deep learning and machine learning, you don't have to put so much manual effort. You can just feed it in a model and the neural network can itself learn which features are important to it. So we will do statistical learning in this module, and in this module, the main goal of is the statistical learning's main goal actually is to make inferences and to understand relationships between different variables. So if you want to understand the relationship between a predictor and a response explicitly, that's where you do statistical learning. And the good thing about it is that you are not restricted in terms of the amount of data you have. So even if you have 50 or 70 data points, you can do statistical learning. And it is very highly interpretable. I mean, it's not like a black box. You know what is going in and what will be the transformation that will come out. So you know the entire relationship of the predictor with the responses. And whereas in machine learning, the focus mainly relies on finding the generalizable model. And the interpretability, as I told you, is very low and complexity is moderate. Whereas in deep learning, the predictions get accurate. That's true. The interpretability goes very low, very, very low. And it can handle very complex patterns, very complex problems. It can learn a whole lot, even sometimes in some cases more than you expect. So we'll go to regression. So regression is what we'll do in this module. We'll try to do linear regression, linear modeling. And regression is a set of techniques. So basically it's just a technique which is to predict a certain response. Like if you want to predict, let's say you have a data set and you want to predict one variable in that data set based on the other variables. So predicting this data set based on those variables is called regression. The techniques that are used to predict these things is called regression. Now, it can be used to quantify the magnitude. So this is quite an important part of regression, that you can actually you can quantify how much a certain variable is affecting your response variable. And different regression models can be used depending on your response, on your data, and everything. And then there are GLMs. GLMs are generalized linear models, and they represent a family of models, and they contain the basic regression models like linear regression and logistic regression, multiple linear regression, but they are generalized. So linear and multiple linear regression, linear regression simply has one predictor and response. In multiple linear regression, there are multiple predictors and one response. So just to make it clear once again, what is the response and what is the predictor? Response is the thing that you're trying to make a prediction on. Okay. And the predictor predictors are the things that help you make a prediction on that response variable. So linear regression has only when the response is dependent only on one variable, and multiple linear regression when the response is dependent on a lot of variables. So this is the mathematical representation of linear regression. It is a simple straight line, y is equals to ax plus b. And in multiple linear regression, the number of variables increase. So it's ax plus b, x1 plus c, x2, and up to as many predictors you want. So this is a very important thing of linear regression. So if these four assumptions are not met, you can't actually apply linear regression at all. So this is quite important. So the four different assumptions are that there is actually a linear relationship between y and x. That means the thing that you are trying to predict and the things that you are making predictions based on. These two things must have a linear relationship. And that makes sense, right? Because in linear regression, you are assuming that the relationship between these things is a linear one, isn't it? So that makes sense. And then the second assumption is that the errors are independent. That means that the errors do not depend on each other. So there is no connection between how far any 2 points lie from the regression line. They are all independent. And also the responses are normally distributed. So this is quite an important assumption because it means that all the responses are normally distributed at each level of x. And then the variance of these responses is equal. There is no invariance in these responses. So these are just four assumptions that you have to keep in mind before you decide on what are you trying to do with your data or what you will do with your data. If these four assumptions are met from your data, from your EDA, you learn that these four assumptions are met, then you can go ahead and apply linear regression. Now, before, as I told you in the beginning, in the introduction of this slide, in this module, that before doing any type of modeling, we have to do some EDA because otherwise we won't know what variables are important and what variables we need to use as filters. So we will use the Palmer Penguins dataset that you guys have been familiar with till now. I think this has been used in all the modules till now. So this will not come as a surprise to you guys, and you can also make connection to it. So you know, okay, so these were the features in that dataset. So now let's try and model something and see what we can do from the dataset that we have just learned. So we will use the same dataset. So the demo for this why are we doing this EDA? Because you have done an EDA module as well, if I remember correctly. So we are doing EDA in this module because we want to find which variables are best to predict the weight of penguins. We are trying to predict the weight of penguins. And for that, we have to do some EDA to find out which variable is important to do that, to allow us to predict that. And also we want to quantify the relationship between those variables that help us in predicting the weight of the penguins. So these are very simple lines of code that I think you guys would know by now. How you load in the libraries and stuff. I'm trying to, okay. So this is how you guys load in all the libraries. All these are different libraries that you might need. And this Palmer Penguins library, this library contains the penguins dataset. And I'm sure you guys know about it by now. Okay, so once we have loaded in the library, so this attach penguins, the first line, it attaches a data set to this. notebook. Then you define penguins as penguins, and then you use this library cable function, and head will show you n equals to 5. So this is the data head of data penguins, n equals to 5. So you show five values, five top values of the dataset penguins. This is what this line of code is doing. And then you provide a caption, forest fire data frame, and you can see the caption here. You can see the caption, forest fire data frame. And then this is a piping operator. I'm sure you guys must have learned about it by now, either in introduction to R or in some module. But this is the piping operator. This allows you to perform a lot of operations on a single thing. So this piping operator means once you have done this penguins, once you have done this thing on this data set, then you go ahead and do this. Then this chunk of code is just styling. So you do cable styling, define the font size, define the width of the table, you define the LaTeX options, and you define the various the way that you want to represent your data. So it's not very important. It's just so doing all this is unnecessary. You can also just type in head and in bracket penguin, and that will also give you these five columns. So that is it. That's the main purpose of this slide, to show you how to see the first few columns. Okay, so now to find out more about your data set, there is a function called str. So what this does, it tells us about the columns that are present, their data types, and some additional information if we need. So for example, if you type str penguins, it says that it is a table, 344 rows and 8 columns. And these are the column names: species, island, bill length, bill depth, flipper length, body mass, sex, and year. And it shows you what are their data types. So species are factor, island is a factor, but you see body mass is an integer. So now we know that we have eight columns in our data set, and we have some of them are factors, some of them are numbers, some of them are integers. Okay, so now let's go ahead and check how much percentage of data is missing. Okay, so there are actually a lot of ways to fill in missing data. Okay, so generally what we do is we don't, if the percentage of missing data is too large, so we don't just throw away the data because it might be important. So what we do is we have various techniques. We might fill it in as the mean of the entire column. So we might fill in the median values of the entire column. So these are various techniques. But in this data set, let's first check how much percentage of data is missing. So what this you're again calling the cable function. Call means is dot na penguin. So this means how many of the data points are na inside penguins, and multiply that by 100. That will give you the percentage. And you print that inside a new column and name the column missing values. And then this is again the same styling that you've seen in the past slides. So what this does is finds the percentage of missing data in every single column. Column means every single column of penguins. NA into 100 gives the percentage, and then you fill in the values in the missing values column. So you see species has no missing value, island has no missing values, build depth has some missing values, sex has some missing values, and so on. So you can see that all columns have less than 3% of missing data. Yeah. So there are, as I said, there are a lot of strategies to handle missing data, but in this case, it's less than 4%, so it doesn't really matter. So we'll just discard them. We'll remove this missing data. Okay, so now that we have done some basic loading in, so now let's do some EDA to check the relationships between the various variables. Okay, so this is a function. So with the below chunk of code, we can examine the relationship, a summary of the relationship between various model variates and responses. So you use the GG pairs function. It asks for the data, and then it asks for the column that you want to see a relationship in between. So we give it the 6 columns that are actually numbers and integers. We don't give it the columns that are not important to us. Okay. So you see, we had 8 columns, right? You have year and you have island. So we don't use year and island because because we figure out that those things are not relevant to the body mass of a penguin. Okay. So this shows the relationship between various variables. So if you see these 3 star marks in the correlation matrix, so bill length in mm is highly correlated to body mass. Okay, then bill depth mm is highly correlated to the body mass. then flipper length is highly correlated to body mass. So we figure out, so the relationship between two continuous variables is depicted with scatter plots below the diagonal. Okay. So inside, so for the continuous variables, you see this is the diagonal, and below the diagonal, this lower half shows the scatter plots of relationship between the two variables. Yes. And then this above diagonal shows correlation values. And we can see that there is a strong correlation between body mass and build length, body mass and build depth, body mass and flipper length. So from this, we can get a sense that these three variables would be the most important in predicting the body mass of a penguin. Okay, so let's get ahead and do some modeling. So first of all, what we'll do some basic linear regression, linear modeling. Okay, so linear regression, no multiple linear, only linear. So one predictor, one response. So we'll check the relationship between each of the bill and flipper variables individually. So first of all, we'll do body mass with bill length. So this is the LM function in R that helps us in prediction. And this is the response that you want to predict. This is the syntax, like what you want the predictors to be. And then these are the predictors. So in this case, we are only using bill length. And then you give the data as penguins. And then this summary of model one function will print out this entire thing. It will show you the call, the formula that you use, the residuals, the coefficient, the significance codes, and the residual standard error, multiple R squared, and so on. So let's make a few observations from this summary of our pet. Now, as you can see, the adjusted R square, this value is 0.3455, which is about 35%. So what this means is that 35% of variability in body mass is explained by bill length included in the model. So, for example, what does this mean in simple language? So, if someone says, okay, you have to predict the body mass based on bill length only. You have this bill length and you have to correlate bill length with the body mass of a penguin. So if you try and model these things, so if you predict your body mass based on only bill length, it will only explain 35, one third of the change. So you will figure out and you'll say, okay, this is not the only variable. Bill length is not the only variable that influences the mass of the penguin. It only explains only one third of it. So there are more variables that come into it. This alone can't explain the entire change of body mass. So that's how you interpret adjusted R square. And then you see the residual standard error is 651.4, which means that on average, if the predicted values are 651 units off from the actual value. So, for example, if given this model, you predict the body mass of the penguin to be 1,000 units, then if your predicted value is 1,000, then the actual would be anywhere in between 350 to 1650. So it would be a difference of 650, right? So it would be either 350 or 1650. It would be anywhere in between that. So that's quite a bit. And you see the p-value. The p-value is another important thing. It means that the model is statistically significant if the p-value is less than 0.05. And if you want to learn more about statistical significance and p-values and S-statistics, then I would recommend this book that I have attached in this module. In this link, you go, and this is an open source book. It is available for R and Python as well. And it will explain it very beautifully. But in essence, what p-value or what statistical significance is. So if you try and model something, if you make a model and then your model is only 50% correct. Okay, so every time you predict something, it's only 50% correct. So it's no good than making a guess, right? Because even if you make a guess, it is supposed to be a 50% guess. So the baseline for your model is 50%. If it is 50% accurate model, then it is basically by luck. The variables that you have used, the formula that you have used is essentially useless because that could have been just luck. So that's what statistical significance means. That if your model has some statistical significance, if is not just based on luck, is not just by chance. So the way to measure that is the p-value. So if your p-value is less than 0.05, we say that the model is statistically significant and it is not just based off pure luck. So that's in short what p value means. Now, we'll try and predict the, we'll try and plot the body mass with respect to the bill length. So what this plot function does is that it plots the bill length with the body mass, and AB line will show a line, the prediction, the regression line that of model one, the model one that we just created, it will plot the line. So you see the model one fit. So the actual values are not very, so the fit is not very good, but it is relatively good for a one variable fit. It's decent, and there also seems to be a hint of non-linearity. So you can see there's a slight parabol shape in this fit. So the actual values might even fall on a parabola, but we don't know yet. Okay, so this is, so now let's move on to the second variable and do the same thing. We create model 2. Model 2 would be based on the build depth only, not build length, not anything, just the build depth. So once we get that, we type in summary, we get this summary as well. And you can see this model is even worse because the adjusted R square is 0.2. So build depth alone can only explain 1/5 of the change in body mass. Okay. And the standard error of this model is also greater than model 1. So, all in all, this is way worse than model 1. But let's see how does this fit shows up against the actual values. Okay, so let's see the plot that we saw for model 1. So if you see in this case, if we do the same thing, we plot build depth and body mass, and we plot an AB, the regression line for model 2. So you will get this line, and these are the actual. So you see, this is, this is, for the lack of a better word, this is trash. This is actually trash because this model is not good at all. Okay, so let's move on to next thing. So we know we had three variables that were statistically significant. Now we do the third one. The third one was the flipper length. So do the same thing, the same syntax, the same thing. We do the summary of and do model 3. Then this will show up everything. Now, if you see the adjusted R square of this model is 76%. That means that flipper length alone can explain almost 2/3 of the variability in this model, which means it's quite good. It's a very important variable. Flipper length is a very important variable. This shows us. And also the standard error is the minimum. It is just 393. So if you predict the body mass to be 1,000 based on this model, so it would be actually anywhere in between 1,400 to 600. Yeah, in that range. So it's not very bad. It's the best out of the three models that we've made yet. No, and that is true as well. If you see the points against, do the same thing, plot flipper length with body mass and plot the regression line for model 3, you see that the regression line is quite in agreement with all the actual points. So this fit is very good, quite good actually. Okay, now we move on to multiple linear regression. So now you have seen that three models are statistically significant. Why? Because the p-value for all those three models was less than less than almost 10 to the power minus 16. So that's almost 0. And this was the case for all the three models. So let's try to combine these variables together to make a better model. Yes. How do we do that? We use the basic R function. We use the same function. Nothing is going to change. We'll just add more variables into the call formula. Okay, so the syntax will be the same, lm y tilde x1 plus x2 plus x. These things will be added now because we have more than one predictor. And now the summary function will output the regression coefficients for all the predictors, not just the one, because it has more than one predictor now. So moving on, if you see model 4, so model 4 will try to predict body mass with build length plus build depth. We are using two variables now, both of these variables together, and then we print out the summary. You see the call formula, you see the residuals, you see the coefficients, and you see the residual standard error and the adjusted R square. R square is 46%, which is not very good. Standard error, almost 600, not very good. Okay. Okay. So what we do is we try to add all the three variables or all of the variables that are available just to see. So once you have done collinearity analysis and feature selection that we talked about initially, and I also showed you collinearity analysis a bit as well in the GG pair slide. where we found out that three variables are highly correlated to the body mass. So if you have done that in feature selection very well, then we can create a data set with only the relevant variables. Okay. That contains only the variables that are important to your response. Okay. We're not doing that, but you can go and learn more about collinearity analysis and feature selection. I've provided link for that. Even you can find it in that open source book that I have linked. Okay, so if we consider, for example, in our case, if we consider that all the variables are relevant and we want to include all of them. Okay, so we want to include all seven of them. So body mass is one and there are seven remaining. We want to include all seven of them as predictors. So maybe that could be very, very useful in some cases. So in some cases, all the predictors might be very important in predicting the response. Yeah, so we don't know. So it would be very tedious to type body depth, like bill length plus bill depth and everything plus plus plus. So the shorthand in R is just to use a period. So body mass tilde period. Period means take all the remaining columns inside the dataset and use them as predictors. So that's how model 5 is created. You print out the summary for model 5 and you see all the columns are used in predicting this. And you see this thing shows you which of these things are statistically significant. And this is quite interesting because if you see the adjusted R square in this case is 88%, almost 88%, which means that, and it makes sense as well, right? Because this is the entire data set and you're using entire data set to predict body mass. So it makes sense that the entire data set would be able to explain 88% of the variability in body mass, right? Because otherwise it would be a useless data essentially. And then you have standard error is also very good, not that bad. P-value is very good, almost zero. That means it's not just luck. This model is significant statistically. But in this case, you have to be careful. This might be a case of overfitting, but that goes beyond our scope. So for now, let's just focus on the good things. That this has a very good R squared value and a good standard error value, and also the P value is very less. That means it is also statistically significant. Okay. So now there is something called interaction terms. So if you use build depth plus build length, it will tell R to include an interaction term between build depth and build length. Okay. But if you use build depth asterisk build length, it includes build depth, build length, and their interaction as predictors. So you don't have to write it like this. Like you don't have to give three different variables. Like you don't have to write, okay, use build depth plus build length plus the interaction of these terms. You can directly say build depth asterisk build length, and it will include these two separately and as well as their interaction in the model. Okay. So model 6 will make use of interaction terms between build depth and build length just to see what if it is useful or if it makes our predictions or modeling better. Okay, so you see R squared it's still 60% and this is 50%, 500, sorry, 500, the residual standard error. So it's not that better. So, and that might make sense because build depth is not a very high variability explaining predictor anyway. Okay, now comes the most important model because this is what we have based everything on. Because we saw in our collinearity analysis that three variables were important in predicting the body mass. Okay, and what were they? They were build depth, build length, and flipper length. But up till now, we haven't used all these three together to include all these three to see how the most important variables stack up as a model. So that's what we'll do now. We'll predict body mass using this, and this. So what this asterisk does is that it uses all these three individually and this respective interactions together to predict the body mass. Yeah. So this shows you all the coefficient that it has used. So it used build depth, build length, flipper length, then interaction of build depth and build length, then interaction of build depth and flipper length, and so on. Okay. So this model explains 80% of the variability and it has 350 standard error, which is very good. I would say which is very good because In that case, we were using all the variables. In model 5, if you remember, it had a better R squared. It had almost 87% R squared. But that might be a case of overfitting, because we are using everything in the data, and that might not even be important. It might be overfitting, and it might not be generalizable. But this data set seems better. This model seems better. Okay, so but how do we know which model is better? How do we make a conclusion out of that? So for that, this is a function called analysis of variance function, or ANOVA in short. So what it does, it is a simple call. You call ANOVA in bracket to give out all the models that you want to test, and it will give you some results. So this is what it gives. It gives the analysis of variance table. Model 1, you use this formula. Model 2 was this. Model 3 was this. Model 4 was this. Model 5 was all the variables. Then model 6 had interaction terms between two. And model 7 had interaction terms between all three highly correlated coefficients. So it gives out this p-value. So according to this, so the above variance analysis will show you that the p-value for three models, that is 5, 6, 7, they have the minimum p-values. Okay, only these three models, in comparison to all the seven, these three models relatively are statistically significant. That's what we can take from here. We won't get into the F statistic yet. We will explain that in the next one. Okay. So from here, you can get that the p-value for these three models are practically zero, which means these three models are statistically significant. And if you recall, model 5 contained all the variables, model 6 contained only the interaction terms of length and depth, and model 7 contained the interaction terms of flipper length, bell length, and depth. Okay, let's go on. So now we'll compare only the three most statistically significant models. Yes, model 5, model 6, and model 7. So this shows you model 1 is all the variables, that is 5, model 2 is the interaction of 2, and model 3 is interaction of 3. So now if you see, only two models are statistically significant, and those are 2 and 3, that means 6 and 7. So only model 6 and model 7 are statistically significant. Also, the F statistic for model 7 is 132, right? So if you just looked at the summaries from the models that we had printed out, summary for every model, you would make a conclusion that model 5 is the best, right? Because it had the best R squared, it had the lowest standard error, and you would conclude that okay, model 5 is the best model. But the ANOVA analysis of variance shows that the model 7 is a statistically better choice than model 5 for predicting body mass. But also, one more thing that has to be said is that statistical significance is not always practical significance. It depends on what you are trying to do with your model, what you are trying to predict, and what is your personal use case. But in general, statistical significance is quite important. So, what does F132 mean in this case? In this case, F statistic of 132 means that this model is more statistically significant than model number 6, and this is a better model, and you will have to, if you consider, so okay, I'll try to explain it very shortly, but it might be a bit confusing. That's why I was trying to avoid it, but let's go. You can read about it in more detail in the textbook or somewhere else. So what happens is that you, for example, when we are trying to measure the variance of these three. We are trying to analyze the variance of these three and trying to measure the performance which is better. So we make, let's say we make a null hypothesis. We assume that, okay, all three models have the same, all three models are the same. None of them is better and none of them is worse. All three are equal. So this F statistic is 132. So that tells us that no, you have to accept that this is the best model and the rest of them are, you have to reject the null hypothesis, and you have to accept that this model is the best one statistically. So that's where we are now. Okay, so that's what we have done. We tried to compare single linear regression of single predictors. We did that for three models, and model 4 was a multiple linear regression of two variables. Then model 5 had all the variables, and model 6 had interaction terms of only two variables. Model 7 had interaction terms of the three highly correlated variables. And you can see statistically that is the best performing one. Now, Let's move on to GLMs. What are GLMs? So in a linear regression model, we have to model the value of a variable y that is continuous and as a linear function of x. Okay. So the structure is simply y is equals to x something plus epsilon, that is the residual standard error. And also, if you remember, I told you in the beginning that you can't use linear regression until four of these conditions are satisfied. Four of these assumptions are satisfied. And these are the four assumptions, a repetition of those four assumptions here. But in real world examples, what you'll find is that all is these assumptions are very easily violated, very easily. So what to do? Then in that case, you have to have some tools that can help you in using linear regression, but then and using linear regression and to bypass these restrictions of the four assumptions, right? That's where GLM comes in. So where linear regressions are not appropriate, GLMs are needed. And GLM is the generalized version. So it allows for deviation from the assumptions that are underlying linear regression. So these take into account the deviance or the deviation from the assumptions. So it generalizes the linear regression by assuming that the dependent variable y is generated from any particular distribution in an exponential family, not necessarily a normal distribution. Okay. And these distributions are normal, might be binomial, Poisson, gamma, any exponential family. So in this way, the distribution of y does not necessarily have to be normal, as I said. And in addition, GLM allows the linear predictor to be connected to y. So the linear predictor is connected to y via link function. So it essentially transforms. So this is a lot of mathematics, but what you have to understand is that essentially model does not have to assume a linear. So now it's not important for the response and predictor to have a linear relationship anymore. What it does is transform the relationship from your response and predictor to a new thing eta. And now what happens is that the model assumes a linear, it still assumes a linear relationship, but not between the response and predictor. It now assumes it between EY and the transformed eta. So that's what you have to, that is, I think that is the takeaway from the slides, that it not only it bypasses the restriction of linear relationship by transforming the variable, okay, transforming the variable and relating it to the same predictor in some other way. That's it. That might be the most simplistic thing. Okay. So when you use GLM, you have to use a link function, and if the link function argument is given as Gaussian, it is equal to linear regression, what we just did. And if we model the data that we had using GLM right now, and we use the family function Gaussian, we would get the same. Other examples of a GLM are logistic regression, Poisson regression, and so on. But that is beyond the scope, and I think that this is enough for this module. So this is the glossary. If there are any terms that you didn't understand, you need an explanation or short definition, you can go through this. And I think that is it. Thank you very much for your time, and I'm sorry if this has taken a bit too long. Thank you.